Welcome back. Yeah, I know I spent probably a little bit too much time putting together that little animation, but it's a lot of fun. Did that a couple of years ago and I like using it. Anyway, the agenda for this little slideshow is chapters 1 and 2, and specifically we're going to do an overview of engineering briefly, talk about this particular course, talk about SI units and engineering notation, voltage, current, power, and energy. Those are our 4 quantities that we're most interested in this course. All right, more agenda items. Circuit elements, those are the actual devices that we're going to connect together. And there's some theory that describes how those devices operate, how to connect them together, and how to build models, the mathematical rules that govern how these interconnected elements behave. And we're going to look at dependent sources as well as independent sources. We'll get into that. All right, so electrical engineering is a broad field, and just starting out as students, most likely you haven't decided what you want to do. You might not even be sure about engineering in general, but there is lots of opportunity to specialize. So there's a lot of engineers that work in communications, and they're dealing with radio waves mostly that are modulated to contain more and more information. You know, simple radio waves, AM and FM radio, like if you still have one of those in your car, and more complicated all the way up to 5G and maybe microwave signals that are used for long distance transmission. So there's a lot of electromagnets, a lot of electromagnetism in that field, and a lot of advanced mathematics and even some signal processing that goes into that. A lot of it's analog. Okay, there's also computer engineering. This is a very large field of subfield of electrical engineering. It tends to be concentrated in particular cities and areas, whereas maybe other kinds of engineering, like power engineering, for example, that's spread out all over the country. That's in this list somewhere. Yeah, power engineering, power grids all over the world, and you know, it's a huge. Power industry is an interest of mine, just as a kind of a hobby or whatever, an intellectual interest of mine. I've studied it over the years, although I've never worked in it. But there's a lot of activity going on in the power industry nowadays. Tends to kind of not get a lot of attention, but it is a huge industry. And it's a huge industry that's undergoing a lot of change, so that provides a lot of opportunity. Anyway, back up, there's control processing, which is, a lot of that's analog. A lot of that's increasingly becoming digitized, but yeah. There's also signal processing, which relates to communications. Anyway, this is all in constant flux, but the point here is that there's lots of different things to choose from, and you don't have to choose today. You know, I'll give you till next week. No, not really. I mean, in life, it's really hard to plan what you're going to do. Just do something that's interesting and keep moving forward in life, and know that there is lots of opportunity. That's my advice. And also talk to lots of other people, get lots of opinions from other engineers and other people that can help you, and your parents. You know, talk to your parents. They know a lot about you and they care a lot about you. Most parents do. Anyway, so the course in a nutshell. Well, for many students, this is the first course in engineering analysis. Okay, so we're learning methodology. We're learning how to think in a particular way. And this methodology is not just limited to circuits. So this is a really important course, all right, because you're learning a certain way of solving problems and setting up things for setting up a problem for a solution in a particular organized and structured way that leads to a solution. In particular, we're going to construct circuit models, and we're particularly interested in voltage, current, power, and energy in this class. All right, so we're learning circuits, but we're also learning an engineering methodology. And so we're going to do modeling. So modeling is super important in engineering. And you might even say that modeling is the most important engineering skill. It might even be what engineers do that defines in what engineering is. Could be. It's super important, all right? maybe the most important engineering skill. So what is a model, or what are the kinds of models? Well, we're going to, well, generally speaking, outside of circuits, there's a drawing is a model. There's other kinds of system diagrams. There's process flow charts, even chemical equations that show up in these kinds of, like a refinery or a chemical plant or a plastics processing plant or something like that. These process flow charts, these are all different kinds of models. Okay, we're going to draw little diagrams, little squiggly lines, circuits. What's a particular kind of model that we're going to draw? Okay, these are the units that we're going to deal with primarily. There's a big list in your book. It's much bigger than this, but these are all derived units, right? In the SI unit system, the metric system, System International, and in my very bad French, there's base units, right? What are the base units? There's time in seconds, there's mass in kilograms, there's distance in meters, and there's a couple others that escape me at the moment. I think something about some kind of light unit in there, like lumens or something. I don't think it's lumens, but there's something related to light. Okay, those are the base units, and every other unit in science in the metric system is derived from these units. The simplest one you could derive is frequency. That's 1 over time, right? Or so it has unit of hertz, has a symbol Hz, and the formula, that is what simpler units does it consist of. The formula is 1 over seconds, or 1 over time. Okay, then there's what's the next one? Force. Okay, and a Newton. That's a biggie. Newton invented calculus and threw force in there along the way. And remember, F equals ma, and from and acceleration is meters per second squared, and m is mass. So you get kilogram meters per second squared, right? So that's a derived formula, the Newton. Okay, if you take a Newton and you apply a Newton, like if you push something, if you take a Newton and you push it a certain distance, then it's a force applied over a certain distance, or a Newton meter, and that's work. You've just done work. If you push an item, right? If you apply a force to it over a certain distance, like slide a brick across the table, you've done work. So that's a joule. Work is a kind of energy. It has units of joules. It has a symbol J, and it has a formula of derived units of newtons, meters, Newton meters, right? Okay, and then if you do work over a period of time, you end up with power, okay, joules per second, or a watt. And then when you're talking about electrical particles, you get into charge, and you can think of electrons as charged particles because, well, that's what they are. And if you had a certain quantity of these charged particles, named after a guy named Coulomb, you'd have a Coulomb. So a Coulomb is just a bag of electrons, is the way I think of it. It's just a certain amount of electrons, a certain amount of charged particles. Okay, and if those charged particles are flowing by you at a certain rate, like you can think of a river of charged particles. I mean, that's what a wire is. It's like a garden hose, or a river. There's this stuff going down the wire, and it's traveling at a certain rate. So the stuff is moving at a certain rate, or there's a certain amount of coulombs moving per second. Ooh, is that an error in here? Coulomb is an amp. That might be an error. You guys look in the book, check me on Coulomb here. I don't want to stop right now and fix that, but check that. It's the rate of flow. A Coulomb is a charge, right? And then amp is coulombs per second. Amp is coulombs per second. So I think a Coulomb might be an amp. I gotta check that. Okay, then you get into energy, or specific energy of charge separation. That's the volt. Because charged particles, opposites attract, right? If you have electrons and protons, let's say, if you were dealing with strictly charged particles, then they attract, right? So if you want to separate them, you have to apply energy. You have to sort of pull them apart. That's kind of the way I think about it. Like, think about a bag of electrons and then a bag of charged positrons or protons, you know. That's not exactly what's happening, but if you think about it that way, if you think about a bag of plus and a bag of minus, they're going to want to stick together. Okay, and you'd have to grab these two bags and pull them apart, and that would take energy. Okay, so that's what a volt is. It's the energy of charge separation, or how many joules need to be applied per coulomb. Okay. Okay, and then lastly there's ohms, which is volt over amps. It's you know, the resistance to flow, or how much energy it takes to get a certain flow rate of coulombs, right? Because you have to, in many cases, you have to push the electrons through a tiny hole, you know, called a resistor, sort of. Or at least that's conceptually a way of understanding it. Anyway, these are the units that we're going to be dealing with, all right, primarily. Let's kind of move on. So in your science classes, hopefully you've seen scientific notation where you have some number times a power of 10. Okay, engineers, we do that, but we like to keep it in groups of 3, which hopefully you've seen this already. But for example, say you have some tiny quantity, 0.000044 seconds. You move the decimal by 3s, and until you get the base number. In this case, 4 is a reasonable, you know, or just a couple of digits. Like we like, I don't know, 1 to 4 digits, something like that. So you move that decimal point over 6 spaces and you get 44. And the first 3 would be milli, and the second 3 would be micro. So 44 microseconds. And likewise, if we had a big number like 87,625,622 volts, that's hard to say. So it's easier to move the decimal point to the left by 6 spaces and make it 87.6 times 10 to the 6 volts, and then use the prefix mega on the units volts. So it's 87.6 megavolts. So we typically round to about 3 digits. If you think about it, that's 1%, which for most kinds of analysis, many kinds of analysis, 1% is pretty good. You know, okay, let me say that again. I mean, three significant figures is pretty good, because when we do these models, we're making lots of simplifying assumptions, many simplifying assumptions. So we don't need to get too picky about the accuracy of our answers, because there's a lot of assumptions that went into that. So if you can get to 1%, you know, you're pretty good. And a lot of times we're interested in just, I don't want to say rough, but just I sometimes call this first principles thinking, just thinking about, is something possible? Like, is the number, like, let's say you work on a problem, you get an answer, and that answer, is it 10 or is it 1,000? You know, is it this huge thing that maybe is impractical, or is it a reasonable number that's possible? That's a lot of times that's the kind of things that we're interested in. Or maybe that's if you're just thinking about whether something's possible at all. But let's say you're building a device and you're trying to find the quantities of the sizes of all the elements, like how big are all the power supplies, and how big are all the wires, and how big are all the resistors and capacitors and things. If you can get to 1%, that's pretty good, because the whole system together is going to interact in weird ways, and almost always you're going to have some way to adjust it. You know, you're going to have some variable elements in there, like knobs, you know, basically variable resistors and things, so you'll be able to dial it in. Okay, so that's kind of the basis of engineering notation. Let me just kind of summarize. You're interested in a couple of things. You're interested in in the magnitude scale. Is something 10, 100, 1,000, a million, something like that. You're interested in that, and then you're interested in getting a number, a final number that's within 1% or so. Okay? And we don't want to deal with a lot of huge strings of digits. We just want to deal with small numbers. All right, so I'm sure you're all familiar with this stuff at a basic level. I hope what I'm saying adds to that a little bit. I hope. All right, let's go on. Yeah, so we're mostly interested in voltage, current, power, and energy. And yeah, let's go through each one of these in detail a little bit. This is the whole class: voltage, current, power, and energy. So voltage, it's the energy of charge separation. It's the work required to separate charges, because remember, opposite charges want to stick together. So the quantity is volts, and it's a derived, no wait, that's the unit. Yeah, the unit is volts, and it's a derived unit coming from joule and coulomb. Okay, the quantity is voltage, and it's a derived quantity consisting of energy divided by charge. Okay, so what I'm saying here is there's a difference between the quantity and the unit. Okay, like, let's take another example, money. Okay, there's this idea of money, but it comes in certain units. Like in America, we use the US dollar, right? If you were in Mexico, you use pesos. You know, if you were in Europe, you'd use the euro, right? So it's all money, but it has different units. So that's what's going on here. There's the quantity itself and then the unit. All right. So I like to think of voltage just like water pressure. I like to think of circuits as, because it's hard to imagine electrons and what's going on in a wire and what's going on in a resistor. It's hard to imagine that because it's very tiny little quantum effects that are happening there. So I like to think about water moving through pipes, because that's much easier to get a mental picture of. Like, you can imagine a garden hose, right? When you put your thumb on the end, you feel the pressure. Okay, so you can think of voltage that way. There's some kind of pressure that's pushing on your thumb when your thumb is on the end of a garden hose. So that's what voltage is doing. Okay, then there's current. So these little electrons are charged particles. Usually they're electrons, but not always. Okay, most of the time they're electrons flowing through wires. But let's take a battery, for example. In a battery, it could be positive ions flowing through an electrolyte, and they'd be flowing the opposite direction. They'd be flowing from positive to negative, whereas the charged particles are flowing. Wait, I mixed that up. I've reversed that. The charged particles in a battery are going from negative to positive, but no wait, they're going from, anyway, they're going the opposite direction. But usually it's electrons, but it could be other things. All right. So is this a unit or a quantity here? This is a unit, right? Amp is a unit. It's composed of the derived unit coulomb divided by second. It's analogous to water flowing, right? Back to, imagine you're out in your your yard, if you have a yard, with a hose squirting the grass. So that's what I do. I have a yard and I water the grass sometimes. So the current is the actual water moving, right? You can have a lot of water moving, you can have a little bit of water moving. You could have a big hose, you could have a little hose. All right, so energy. Okay, now it starts to get more difficult. Energy is a weird thing. It's hard for us to intuitively define. In fact, the great legendary physicist Richard Feynman, who was no dummy, stated this: It is important to realize that in physics today we have no knowledge what energy is. And that was like in the 80s or 90s he said that, somewhere in that area, plus or minus 20 years. We do not have a picture that energy comes in little blobs of a definite amount. And so this guy was a pretty smart dude. And he had a hard time. Newton. You guys remember Newton? Isaac Newton, the guy that invented calculus along with Leibniz. It's story with Newton there. The joke there is that, people picked on Newton because he was a little bit weird. He was a little bit of an outcast, and, he was a nerd. And before it was cool to be nerds. It's cool to be a nerd now, but anyway, they made fun of him, and so to get back at the world, he invented calculus. So, that's why we have calculus. So Newton didn't really even understand energy totally. He didn't really deal with energy a lot. That came later. And Newton was a pretty smart dude too. So energy is a very hard thing to get a grasp on, but we need a better definition, all right? So here's the way I think about energy. Okay, energy comes in interchangeable forms. The easiest form to understand is probably work. Okay, so once again, back to the brick idea. If you have a brick sitting on the desk or a book, take your textbook. Do it now. Take your textbook and put it on the table and push on it and slide it across the table. Okay, did you do that? I'm sure you did. Well, you just did work. You applied a force to an object, a force in newtons, and you pushed it a certain distance, and you end up with a joule. A joule is a Newton meter. So that's a pretty easy to understand idea of energy. To me it is. So there are other forms of energy that are much harder to get a grasp on. And some of those are heat energy, kinetic energy, that is the energy of motion. There's energy in chemical bonds. There's electrical energy that we're going to deal with. There's the energy in the nucleus of an atom, nuclear energy. There's all these weird forms of energy, but they all have the same unit. They're all joules. And most of these I think all of these, there's a way to convert one form of energy into another. So this works for me. I think about work, the form of energy work, which is very easy to understand, and then I keep in mind this idea that there's these other things that have energy in them that you can transform, all right? So back to the book. Imagine pushing a book. You could push it fast, you could push it slow. Right? You could slide that book across the table quickly, you could slide the book across the table slowly. The amount of energy is going to be the same, but the power is going to be different because of the time you took. Okay, so power is the rate of energy used. So it has units of watt or joules per second. So you can have high power and you can have low power with the same amount of energy. So consider a gallon of gasoline. So a high-powered rocket like Falcon Heavy or something, which doesn't use gasoline, but let's say it did, it would use up that gasoline in a second. Actually, it'd use it up in a microsecond. But that would be high-powered. Okay, but that same gallon of gas could be put in a scooter and you could drive for a long time. Okay, so 1 gallon of gas represents the energy, but if you used it really quickly, that's high power, and if you use it really slowly, that's low power, all right? So more about power and energy. So energy and power are always conserved, at least in what we call classical Newtonian physics. That is, electrical energy can be changed into heat energy, and that's going to happen all the time in this class. That's what resistors do. And then electrical energy can be changed into mechanical energy. That's what a motor does. And mechanical energy can be turned back into electrical energy. That's what a generator does. And like a solar panel takes energy in light and converts it into electrical energy. So it's changing forms. There's usually some efficiency involved in that. Like a solar panel, for example, something like what? On the order of 20 to 30%, somewhere in that ballpark of efficiency, which, by the way, is talked about way too much. It doesn't matter. I mean, so let me say that again. Let's talk about a solar panel. So they use the number approximately 30%, something like that. So there's a certain amount of energy hitting a square meter of the Earth's surface. I think it's something like 1,000 watts. It's something like that. But a typical solar panel will be on the order of 250 watts, 300 watts. So it's about 25%. That's the number they keep throwing around, like it makes any difference. It doesn't. Well, the only number that matters is dollar per watt, right? How much does that watt cost? That's all that matters, because once you reach about 20%, 30%, that's enough. Like, I have solar panels on my roof, and it's about a third of my roof. It powers my whole house, and it powers my car. So, and that's a third of my roof. So I have basically 3 times as much area on my roof as I need to run my entire house. If I covered my whole house, that energy produced would cover the energy I use for my whole life. It would cover the energy I use at work and the energy you use to produce many of the things I buy. So the area efficiency, the energy per the amount of the energy that you're getting out of the area, that 30%, is not so important. What's important is how much does that energy cost per watt. And right now, I think the lowest rates are like $1 per watt, $1.50 per watt, something like that. That's the number that matters. Anyway, so energy of one form can be turned into an energy of another form, but it's never created or destroyed. That is, in classical Newtonian physics, it isn't. Now, a guy named Einstein came along and figured out that, hey, you can turn mass into energy, but we're not going to deal with that. Although, that comes up, I'm talking about nuclear power, of course. There, you're actually turning mass into energy there. But energy in our analyses often leave our system boundary. That is, electrical energy is turned into heat energy, and that heat energy leaves the system. Likewise, we might have a power source, not ideal power source. The power is coming from somewhere, but it's coming from outside of our system. Okay? So, once again, the energy is never created or destroyed. It just changes form, but it does leave the system boundaries. It comes into our little model in the form of, mechanical energy coming in and turning a generator or whatever, and then it runs through resistors, and the electrical energy is turned into heat, and then that heat leaves our system. Okay, these are our power formulas. P equals IV, so power equals voltage times current. And if you take Ohm's law and solve it a couple of different ways and then plug it back into P equals IV, you get 2 more formulas that are useful. You get I squared R and V squared over R. Right? Let's look at the circuit elements we're going to deal with. So we're going to deal with voltage sources, current sources. So these are things that take energy, or power if you want, from outside of our system boundaries usually, and turn it into electrical energy in the form of voltage and current. Then we have resistors, which, speaking of energy, they take our electrical energy and turn it into heat, which leaves our system. Then we've got capacitors, which just store up energy in the system and then re-release it at a later time, and inductors do the same thing. Okay, so we've got energy coming into the system with these sources, leaving the system with these resistors, and bouncing around inside the system with these capacitors and inductors, storage devices. Here's a voltage and current source. In a little more detail, a battery is a very good example. It has a little symbol, a circle with a plus and a minus. Okay, in our analysis, we're going to consider these to be ideal sources. That is, we're going to give them a voltage like 12 volts or something, or I guess this is a 9-volt battery. We're just going to assume that it always puts out 9 volts. Okay, that's an ideal independent source. In reality, batteries don't behave like that. In fact, no source behaves like that. Okay, so that's why if you can get 1% in your answer, it's great, because we're assuming that the voltage source is ideal. That is, ideal meaning it always puts out 9 volts, but it doesn't. The voltage is dependent on the current flow in almost any source. Well, the simpler sources more so. The more elaborate sources can approach ideal. Like many of you may have built a computer. You have a power supply in that computer, right? Big old, like I got a big old, time to brag, a 750 watt power supply, because I love power, and you know, power is my graphic card, so I can sling pixels all over the screen and record videos and play video games. But it behaves like an ideal source. That is, it puts out a couple different voltages, 12 volts, 5 volts, maybe some others. And those voltages are pretty much constant. So it's close to an ideal source. But many other simpler sources are not ideal. Anyway, these sources are going to apply voltage in certain waveforms. That is, in certain changing over time. So we have a direct source, which is just a constant voltage, if you're talking about voltage sources. Then you have alternating voltage sources that kind of go up and down, positive and negative. Then you have function driven, that is, they have a certain what's more complicated waveform, like a pulse. A pulse is going to be very common, or it could be a decaying exponential curve or something like that. Okay, then you have independent sources and dependent sources. So you can think of this battery as an independent source. But there's also dependent sources, which are diamonds in the symbol. They're a little diamond figure in the circuit. A dependent source produces a voltage, if it's a voltage source, that's dependent on some other signal. So you might be measuring some current or voltage somewhere else in the circuit, and then producing a voltage that's somehow related to that. Like usually it's just proportional. Okay, a good example of that, if you've fiddled with cars at all, is an alternator. The charging system in your ICE car, your internal combustion engine car. So there's the bus voltage, which your car tries to maintain at 14 volts. That's a good voltage for charging the battery. That's why they keep it there. So it wants to maintain 14 volts, but the alternator is spinning to do that. And the engine speed changes all the time. Plus the loads on the bus change. Like you turn the lights on, turn the headlights on, turn the stereo on, the loads change. So you have to adjust the output of the alternator to keep it at 14 volts. So the way they do that is they monitor the bus voltage. They monitor the bus voltage, and as it goes up and down a little tiny bit from 14, there's a current source in the alternator that correspondingly adjusts. So if the bus voltage starts to drop, there's a dependent current source in the alternator that will rise a little bit, and that will bring the bus voltage back. So it's once again, in the alternator there's a dependent current source, which would be a diamond in our little diagram, and it's putting out a current that's inversely proportional to the bus voltage. The bus voltage is the voltage available in the car for use. Okay, so that's a dependent source, and there are others that we'll see. All right. Okay, we're going to talk about resistors. This is some little pictures of a resistor. This is a one with stripes on the top. Is a very common package that resistors come in. The stripes tell you the value. Inside, it's very often a little carbon film that provides a very small area for the current to travel through. So it takes energy to push the current through this device, and that energy is turned into heat. You can think of this as like a valve. And then the symbol is a little zigzag. Yeah, they resist the flow of current. Yeah, it takes energy to push the current through them. This free energy is turned into heat. That's it. Oh, it's like a faucet. Oh, and then there's the equation that governs the relationship between those three quantities. It takes a certain amount of voltage to move current, and that voltage is I times R, or you could solve it for I equals V over R. So the rate of flow I is V divided by the voltage. Okay, it's just relating how much energy it takes to push current through a small thing. Okay, then we've got a capacitor. This is a storage device, really. The top picture is a typical package of a electrolytic capacitor. That is, it's some films that are wound up into a cylinder, and then there's some electrolytic goo in there. And so there's two conductive plates and then a insulator or dielectric. And there's a symbol at the bottom with the straight line and the curvy line. That indicates a polarity. We're not going to deal with polarity very much, but electrolytic capacitors do have a polarity. That is, they prefer the positive terminal to be one of those sides, and I don't remember which one because we're not going to deal with it. But let's see. So these things store up energy. Okay, and that energy is related to the charge that's in one of the plates. Okay, so there'll be charge collecting in one of the plates, and then there'll be lack of charge in the other plate, or they call that holes, which is kind of weird, positive holes, but that's the theory. And so the rate of the current, that is the rate of charged particle flow, the current I, is proportional to the rate of change of voltage. Okay, so I equals C dV dt, and C is just the constant of proportionality. It's what we call the capacitance in farads. Okay, so C is the capacitance in farads, and dV dt is just the rate of change of voltage. So what that means is that if the voltage is constant, the derivative of voltage will be zero, and there will be no current flow. But as the voltage starts to change, the rate of change, that is how fast the voltage is changing, will produce a current I, dependent on C, the size of the capacitor. Okay, and we call I the displacement current because there's an insulator in there. That little blue layer is a dielectric or an insulator. The electrons cannot pass through that. So the current that comes in or out of this thing is just coming from the plates. It's not actually passing through the device. So if you want to get current out of this thing, you have to get current into it initially. Okay, it's a storage device. Yeah. Okay, then there's an inductor, which is also storage device, and it's basically a coil of wire, and there's usually some kind of core. In this case, there's a iron core. And okay, there's a lot of electromagnetic theory using the right-hand rule of electromagnetic waves. Right? For every current, there's an associated electromagnetic field, and for every electromagnetic field, there's an associated current. Okay, we're not going to get into that theory. That's upper division circuits where you deal with electromagnetism. We're only interested in charge. Okay, so we're going to look at the charge effects, that is the voltage, current, power, and energy in this device. Okay, even though there is electromagnetics in this device, that's how it works, but we're going to abstract that and use theory that just talks about the charge effects. So this thing stores up and releases energy depending on change of current. Okay, so the equation is V equals L di dt. So the voltage that this thing produces is proportional to the rate of change of current. So what that means is if there's a constant current flowing through this device, it behaves like a wire. That is, the voltage will be zero, because the derivative of the current is, if it's constant, is zero. If the current is constant, the derivative is zero. So the voltage will be zero. So it's acting like a wire. But if the current starts to change, starts to increase or decrease, then the derivative will be non-zero and you'll get a voltage. Okay, so it's acting kind of like a resistor does, but only when the current is changing. Okay, so you can think of this as an energy storage device, because if the current is constant, it's just sitting there, but when the current starts to, say, decrease, it'll put out a voltage. It'll start releasing energy proportional to that rate of change of current. Okay, so we're just dealing with the voltage and the current, V and I. L is the inductance in henries. It's just the size of the inductor, but there's no magnetism units in here. Okay, so there's magnetism involved, but we're not considering it. That's upper division. It's harder. You see that later. Okay, so those were the elements. We can wire up these guys together, and then there's theory that describes how these elements behave when they're interconnected. We call that circuit theory. All right, so a circuit is a mathematical model that approximates the behavior of an actual physical system. Remember, we want to get within 3-4 digits of a quantity, and that's close enough because we're looking for an approximation of an actual physical system. All these elements are ideal, by the way. Let me back up a bit. This L equals di dt, V equals L di dt. Isn't that pretty? How do you get that out of a coil of wire and a magnetic coil? Well, you work really hard at it. So to get this pretty math, there's people that spent a long time to design a device that behaves like the math. The same with this thing right here. I equals C dV dt. Nice, pretty little formula. They spent a long time designing a capacitor that behaves like this formula. The same thing with this resistor, V equals IR. R is a constant. It's hard to get R to be a constant. Okay, so we've designed these devices to fit our math. Okay, Newton came up with this stuff, calculus, which is really useful. And so somewhere along the line they decided, let's make these elements obey the math, and then if we do that, we can make all this circuit theory. Okay, so the point is the actual devices they're not perfect. They don't follow the system perfectly. They're close. Okay. Also, we're only dealing with charges. We're only dealing with current, which is the rate of flow of charge, and voltage, which is the energy of charge separation. That's just charge. And then there's energy that comes out of that, out of the current and the voltage. And then there's the rate of that energy, it's power. It's all charge effects. We're not interested in magnetism, although magnetism is in there. Okay? We're also making a lot of assumptions to make the circuit solvable. So these are important, you know. If you don't consider this stuff, if you don't consider the modeling simplifications you're making and the real world implications of that, you're not doing engineering. You're just doing math. Okay? So you know, we're trying to deal with the real world in the end. And the real world is complicated, so we build a simplified model of the real world. We do some calculations, we come up with some numbers, we build stuff. Then that stuff might not work, so that's why we test it, right? Because we make so many simplifying assumptions so that we can even come up with any kind of answer at all, that you build something, you have to test it. And then sometimes the rocket blows up. In fact, most of the time it blows up. If you've been following SpaceX's progress lately, which I'm a big fan of, they've blown up a lot of rockets. Okay, so these simplifications are important. That's what engineering is about. All right. One of the effects is we're talking about, we're using a lumped parameter system. Okay. What does that mean? It means that, let's say you have a voltage source and then you have a resistor connected. Something might change in the voltage source and it's going to have an effect on the resistor. We assume that those effects occur instantaneously. That is, we ignore the time that it takes for the current to flow through the wire, which takes a certain amount of time. It's traveling at approximately half the speed of light, right? Which takes time. So we ignore that. We assume that the effects happen instantaneously everywhere. Okay, let me give you an example, two examples of where that assumption fails. One is power generation. You have a power plant somewhere far away from the city where nobody has to look at it or think about it. And then 300 miles away you have the city. Okay, that's a significant amount of wire in between these two devices. So the change in the power plant, or the change in the load, that is the city, don't happen at the same time. Okay, so when you're dealing with something like the power distribution, this assumption starts to not be okay. You have to consider effects of items, separated over distance and time. Okay, but we're going to ignore that for much of our analysis. We're going to assume that when something changes in one element, it changes in the other element. Okay, another example of where this assumption fails is in very tiny circuits, like a microchip. Have you noticed, if you've followed clock speeds over the decades in computers, I've been following that. Clock speeds used to be in the kilohertz. Then they went into the megahertz, and now what are they? Something gigahertz. Gone up a lot, but they've slowed down in recent years. And part of the reason is if you have a signal that's being generated by a clock on a chip and it's super duper fast, that signal has to travel all over the chip. And even though the chip is, say, a centimeter, it can take a considerable amount of time for that clock signal to get to the other end of the chip. You could work this out real quick if you want. Figure out the time. Take say a 1 gigahertz signal. Invert that. That's the time that it takes. Figure the speed of light. Okay. Figure how long that signal could travel before it's out of phase by a significant amount, and it's not far. Okay, so you're starting to reach, with chip clock speeds, and you're starting to reach the the physical fundamental limits of how fast a clock can be. So that lumped parameter assumption is no longer a good assumption. Okay, but this is a first semester first semester circuits class. We're just going to assume lumped parameter system. But keep in mind, this stuff matters for the real world when you apply your models to something in the real world. All right. Next assumption is that the net charge on a component is always zero. So what that means is, for a capacitor, for example, if there's a negative charge on one plate, that the positive charge on the other side is equal. Okay. In real life, it doesn't always happen. There's losses in the device. Okay, so it's good enough for solving the model, but there could be cases where that matters in the real world, like if you were trying to make a supercapacitor for energy storage, that might start to come up. Okay, also the magnetic coupling or the magnetism that's in an inductor, or actually in other devices, but much smaller magnetic coupling, but an inductor has a lot of magnetic field around it. If you put two inductors together in close proximity, like right next to each other, the magnetisms are going to intertwine. We call that magnetic coupling. So the magnetism in one inductor is going to affect the other inductor. Okay, that messes the circuit up, and we're going to deal with that a little bit. We have some models that deal with that, but for the most part, we're going to assume that there's no magnetic coupling between components. Okay, if you look at a circuit that has a lot of inductors in it, sometimes you'll see that they put shielding in there. They put little metal wrappers around the inductors to make them behave like the math, right? Because they built a circuit model assuming no magnetic coupling. Then when they build a circuit, they have to shield the inductors so that they actually are not magnetically coupled, so that they behave like they were designed to behave. All right, that's an example of the model not fitting the reality. Okay, also we assume that conductors have no resistance. So a wire has no resistance. In real life, wires have a little bit of resistance, and sometimes it matters. Once again, with power generation, if you have a 200-mile long wire, you need to account for the resistance of the wire. It has a significant resistance. So, all right. Lastly, that we assume that our resistors obey Ohm's law. We assume that inductors obey the derivative law that they obey, and we assume that they obey them, although those are approximations. Okay, here's a simple circuit model. Simple circuit model. Let's consider a little flashlight here. So the battery is an ideal voltage source, and a lot of times we'll use a circle with a little plus minus, but here we can, if we're interested in the fact that it's an actual battery, you use this little symbol for a battery. And why would you use one versus the other? Well, if you think that the simplifications that we're making for an ideal source are going to be a problem, you might want to use a little battery symbol so that you and other people know that you're talking about a battery which has particular, which is not ideal in particular ways. Okay, I think I'll talk about that in one of the examples that I'm going to work, how a battery is not ideal in many ways. It's not an ideal voltage or current source in many ways. All right, so that's the battery. Then there's a little switch to turn the thing off. And then the light bulb, we've drawn a little symbol that looks like a light bulb, but you could also use a resistor. Okay, if we were in normal class, I would do a little example here, but I'll do that later. So the battery is considered to be an ideal independent voltage source. In reality, it's not. That is, let me say that again. So we assume it to be ideal in that it puts out a certain voltage constantly. That's ideal. Like, let's say there were 2 D cells in this mag light. That would be 3 volts. Ideal. But the reality is when you turn the switch on, the voltage drops a little bit. It might go down to 2.8 or something if the batteries are healthy. Okay, and yeah, so it's not ideal, but it's close enough. We assume that the resistor is ideal. That is, we assume that the resistor, the light bulb, obeys Ohm's law. And it only approximates Ohm's law. You know, as it gets hotter, the resistance increases. So the resistance is heat dependent. Also, at a certain voltage, the R will change. So the resistance can even be voltage dependent. Okay, so these models are approximations. You have to build the thing and test it and see if it actually works. We assume that the wire between the battery and the light bulb has 0 resistance. That may or may not be true, especially at the switch. Switches tend to have high resistance. Take one apart and look at it. You'll see that the connection points are very tiny. Yeah. So we're going to apply Ohm's law and Kirchhoff's laws and power laws and yeah. Okay, so just to sum up, you know, a real battery is not ideal. I think I'll talk about that in more detail in this first problem. So this first problem I'm going to post, or maybe it's the second problem, I'm going to wander around into batteries a little bit just to talk about how they're not ideal is really the point that I'm making. It seems like I'm rambling. Yeah, the resistor is not ideal, the conductor is not ideal, especially in the switch. Okay, there can also be other effects that we're ignoring, like there can be a little bit of capacitance and inductance in the circuit. A flashlight, not so much, but have you heard of monster cable? So there's a stereo, if you're into hi-fi stereos and you want to hook up some speakers, there's this cable you can buy that hooks up your power amp to your speaker. I got that. I got these big old speakers that, you know, I like to play really loud rock and roll. And I, less so in recent years, but, you know, I'm getting old. But anyway, the wire that you hook it up with is designed to minimize the inductance and the capacitance. Because think about a 2-conductor wire. It's a little bit like a capacitor. You've got 2 metal things next to each other. That's how a capacitor is built. So a wire has a little bit of capacitance. Also, a long wire is going to have a magnetic field associated with it, right? So that the magnetic field in one wire is going to, you know, permeate the second wire and affect that. So a real-world wire has a little bit of inductance and capacitance. At least that's the marketing that the monster cable people use. And so they've designed their cable supposedly to minimize inductance and capacitance. You know, whether it does or not, you know, I don't know, but it looks pretty anyway. Okay, so that's the idea of real versus ideal. Okay, a lot of material, long video. I hope you got something out of it. I'm gonna work some problems. Most of the rest of the class is going to be a little bit of a brief theory, introduction to each chapter, and then we'll just work problems. All right, thanks.